Hello there! Imagine the following scenario. It's year 2035 and you're floating in your Starship cabin, patiently waiting in low Earth orbit. It launched a few days ago, and finally, you hear the announcement that the ship has been fully fueled and will be leaving Earth's orbit within a few hours, and then onto its destination, Mars. But suddenly, the alarm starts to scream and you see the crew panic for a brief moment. You check your monitor, and you breathe out with both relief and disappointment. You will live, but the expedition is cancelled. All that planning, all that engineering effort was for nothing, because a 1 mm piece of orbital debris hit one of the Starship's tanks. What I just described will be a real mission threat, but since this channel is not for storytelling but for engineering, we will try to figure out what the problem is, how to deal with it, and how is it done in practice. Let's dive into this.
Stage one is landed. LV1, the Falcon is landed.
There is a term for all the small objects which can accidentally hit a spacecraft or a space station. Micrometeoroids and orbital debris, or MMOD for short. Micrometeoroids are of extraterrestrial origin and range from dust particles to small rocks left by comets. Orbital debris, on the other hand, is of human origin, and it can be anything from flakes of paint to depleted rocket stages. Generally, orbital debris larger than 10 centimeters is successfully identified, catalogued, and tracked. This is a great visualization of these identified objects over the decades. When such a piece of debris gets close to the predicted path of a satellite, spacecraft, or the International Space Station, the craft will perform an evasive maneuver using its engines. The tracking system, database, and the organization around it deserve their own dedicated video in the future. So in this video, we will focus only on the small, untrackable objects. The problem we are facing is beautifully visualized in this European Space Agency's video. Each one of these dots is a tracked object over 1 meter large. Now it's all objects larger than 10 centimeters. What a significant step in object density as we switch to objects larger than 1 centimeter. These additional objects are estimated from models because they are too small to be tracked. And finally, everything larger than 1 millimeter. What a crazy mess in all the important orbits, but especially in the low Earth orbit. The Earth is barely visible through all the dots. Alright, so what's the deal? What happens when the spacecraft is hit? The problem is that the average speed of orbital debris impact is around 10 kilometers a second, slightly higher than the orbital velocity. With the micrometeoroids, the problem is even bigger because the average speed of impact is at 20 kilometers per second. It is difficult to intuitively understand what it means and how much energy is involved in such an impact, so let's take these numbers and plug them into a few equations. We can go back to the story from the beginning of this video. Assuming that what hit the Starship was a 1 millimeter diameter sphere made out of steel, traveling at 10 kilometers per second, how much kinetic energy does such a tiny piece of debris have? We need a new napkin. The kinetic energy is computed as Ek equals to 1/2 times mass times velocity squared. While it is proportional to the object's mass, it is quadratic with respect to the velocity. We know average speed of a hit is around 10 kilometers per second, but we don't know the mass of the 1 millimeter sphere, so let's compute it. The mass m equals the volume times density. It is a sphere, so the volume is 4/3 of pi times radius cubed times density. The radius r is 0.5 millimeter, 0.0005 meters, and the density of steel is roughly 8,000 kilograms per cubic meter. When multiplied, we get a mass of 4.2 milligrams, which is 4.2 times 10 to the power of minus 6 kilograms. Now we can put the mass of the sphere into the formula for kinetic energy, and we get 1/2 times 4.2 times 10 to the power of minus 6 times 10 to the power of 4 squared, which becomes 2.1 times 10 to the power of 2, which is 210 joules. This is a number, but what does it mean? Well, for comparison, let's compute the kinetic energy of a baseball during the fastest ever recorded baseball pitch. A baseball weighs around 145 grams. The record throw was measured at 105.1 miles an hour, or 161 kilometers per hour, which corresponds to 47 meters per second. We plug this into the same equation, and the kinetic energy of this record throw is 1/2 times 0.145 times 47 squared, which results in 160 joules. So this tiny steel speck has more kinetic energy than the fastest ever pitch with a baseball, which weighs 35,000 times more. What's even worse though is that in case of impact, all this energy is focused on a very small spot. Let's do a thought experiment. What if we are given a cheat code that will make the steel pressure vessel absolutely unbreakable? Problem solved, right? Well, the kinetic energy of the debris cannot just disappear when it hits the wall. It will get converted to heat. And how does 210 joules of heat look like? As before, the debris is a 1 mm sphere, and it is hitting a 3 mm thick Starship wall. Since this is a back of a napkin math, let's just say that the wall area affected by the hit is a 2 mm by 2 mm square, and both the debris and the wall are made out of 304 stainless steel. So we have 210 joules of heat, which will heat up both the debris and the affected part of the wall. The change in temperature can be computed as T equals Q divided by Cm, where T is the change in temperature in degrees of Kelvin or centigrade, Q is the added heat, and C is the specific heat capacity of steel, and M is the mass of the steel. We know the value of Q, which is 210 joules. The C for 304L steel is 712 joules per kilogram Kelvin. By the way, the specific heat capacity denotes how many joules does it take to increase the temperature of 1 kilogram of material by 1 degree Kelvin. The total mass is the sum of the debris plus the mass of the 2 by 2 by 3 mm of the affected wall, resulting in approximately 0.0001 kilograms. Plugging these numbers into the equation gives us 210 divided by 712 times 0.0001, which results in temperature increase of 2949 kelvins. Well, here is the problem. The 304L stainless steel becomes a liquid at 1727 degrees Kelvin. In fact, after doing a little bit more math, those 210 joules hitting area this small will almost turn the steel into vapor. So even with those cheat codes that will make our steel physically unbreakable, we will still end up with a liquefied or vaporized hull. And do not forget, we are still talking about a tiny 1 mm piece of debris, but we can be hit with untrackable objects that are thousands of times heavier. This is an example of a hypervelocity impact into a thick chunk of aluminum and the projectile that caused it. As a rule of thumb, the wall needs to be at least 4 times as thick as the size of the debris. So for example, for 1 centimeter sphere, you would need 4 centimeter thick wall, and this would weigh so much that no manned space station could ever be lifted to space. If only there was a way how to spread out the energy of the hit onto a much larger area, so that the bigger region of the wall can absorb the heat without melting. In real life, when a piece of debris hits a thin wall, it gets easily through, but the thermal and physical shock turns the solid projectile into a mixed cloud of solid, liquid, and vaporized debris. Wait a second there. In order to break and disperse the debris to stop it from penetrating the pressure vessel, we first need to let it penetrate the pressure vessel? What if we put a thin wall, let's call it a bumper, in front of the actual wall? The projectile would hit the bumper and get through, but break up in the process. When it hits the rear wall, the impact energy would be dispersed over a much larger area, and the pressure vessel would remain intact. Congratulations to us! We just reinvented the basic Whipple Shield, which Fred Whipple published in 1947 in an article called Meteorites and Space Travel. Let me repeat that, in 1947. This slow motion video shows a 2.8 mm aluminum sphere hitting a very thin bumper and rear wall, both around only 1 mm thick. While a comparable single piece wall would have to be at least 4 times thicker than the diameter of the projectile, the total thickness of the Whipple Shield can actually be thinner, thus making the shield much lighter. Since Fred Whipple's original paper, a lot of effort across many organizations was put into improving the basic concept with a goal to stop even larger pieces of debris. What they generally came up with is called stuffed Whipple Shield. The improvements come from additional soft layers stuffed between the bumper and the rear wall, which further break up the debris and slow down the expansion of the debris cloud. Let's talk about the International Space Station. The ISS is impacted by debris quite often. Let's listen to the experience of the NASA's astronaut, Garrett Reisman.
There's a couple of times I was inside the space station, I heard us take a hit. So I heard the ping, but fortunately I didn't hear the ping followed by the psh.
Perfect. This is how much damage the radiators on the ISS suffered over the years. But throughout its 22-year life, no orbital debris has ever penetrated any habitable pressure vessel. How is it possible? The answer is, of course, that the habitable sections are protected by very robust versions of a stuffed Whipple Shield. Here are the examples of the Whipple Shield configurations for the most exposed and critical areas, as designed by the partners NASA, JAXA, and ESA. They all use a similar standoff distance between the bumper and the rear wall of around 12 centimeters, and multiple layers of Nextel and Kevlar in the stuffed layer. The Nextel is used for reduction of the thermoshock, while Kevlar is there for its well-known additional ballistic protection. Each one of these configurations is capable of stopping a 12.7mm aluminum sphere traveling at 7 km per second. This projectile has over 300 times more kinetic energy than the 1mm projectile from our Starship example, and these Whipple Shields can stop it. But how do we know that a particular configuration can stop a certain size of a projectile? I think there are three aspects to this: the experience of the people who design it, computer simulations, and testing. And I cannot talk about the experience because I don't have any. Regarding simulations, there are multiple tools available, both in the term of actual computer simulations and also simpler equation-based calculators. These calculators can give you plots for projectiles' mass and velocity, like in this example. If you are under the curve, you're safe. It is interesting to see the dip here, showing that a slower projectile will actually penetrate the Whipple Shield better than a faster one, possibly because the impact at smaller speeds is not devastating enough to break up the debris. Unfortunately, none of the tools seem to be freely available. Regarding the testing, well, that is the fun part, because to get 12.7mm projectile to the speed of 7 km per second, which is roughly 8 times the speed of the rifle bullet, requires a very big specialized gun. Properly big. A regular gunpowder system cannot provide the velocities needed, so this gun uses a system called two-stage light gas. This old NASA's video in horrible resolution shows how it works. A somewhat regular-looking cartridge consisting of gunpowder and projectile is loaded and fired. However, the projectile in this case is a piston, whose goal is to compress the gas, generally pure hydrogen, in front of it. At the end of the first stage is a rupture disk, which is designed to burst at very high pressure. When that happens, all that compressed gas in the first stage quickly expands and propels the second cartridge with the tested projectile to extreme speeds. Finally, this projectile hits the tested Whipple Shield configuration, and high-speed cameras record the event. I want to note two additional things here. First, the experiment is done in vacuum. The friction of the air at these speeds would ruin the experiment. Second, the reason why hydrogen is used is because the gas expansion rate depends on two things. The first one is the speed of sound in the gas, the second is its temperature. In hydrogen, the speed of sound is 3.8 times faster than in the regular air, and the high temperature is simply reached by compressing the gas in the first stage. Alright, we know how to design and test a Whipple Shield, but due to the weight constraints, it's usually impossible to put the most robust configuration all over the spacecraft. That begs a question: what is the usual process for deciding which configuration goes to what location? And how is the overall safety evaluated? This is of course a larger topic that would make this video too long. But this is Spaceflight Explained, so let's jump right into it. I will use the International Space Station as an example, but similar process can be applied to all spacecrafts and satellites. Everything starts with the mission requirements, which include the mission duration and the acceptable levels of risk. For example, the interesting requirements for MMOD protection on the International Space Station are: Number 1, overall probability of penetration of the ISS shielding of less than 24% over 10 years. Number 2, comply with the ISS catastrophic penetration probability requirement of less than 5%. These mean that based on the size and density estimates of the MMOD in the orbital path of the space station, the maximum allowed probability of penetration must be under 24% over 10 years, and only 5% of the potential penetration cases can result in the death of one or more crew members. Every single piece of surface on every single ISS module is evaluated with respect to the exposure to the debris and how critical the hardware is. This is a visualization of the shielding on the ISS. Each color represents a different configuration. Saying that there are a few different Whipple Shield configurations on the ISS would be an understatement. These speed estimates are all based on the assumptions about the size, speed, quantity and direction of the debris at a given orbit. Since only the objects larger than 10 centimeters can be tracked, it relies on continuously updated models of spatial density of debris and so-called flux for micrometeoroids. In this example for orbital height of the ISS, you can see the average number of debris pieces larger than 1 centimeter per cubic kilometer going over the years. The sudden increase in red and pink are caused by a satellite collision and a missile test. The MMOD risk is proportional to the spatial density of the debris. NASA has developed a tool called Ordem, which stands for Orbital Debris Engineering Model, which provides the data and models for micrometeoroids and orbital debris. These are then combined with the spacecraft's CAD models, the Whipple Shield configuration, and the impact test data in a tool called Bumper, which then outputs the probability of failure. So after these tools are applied on every single Whipple Shield section of every module, the risks are individually estimated and combined together. The resulting failure rate must satisfy the mission requirements. If not, back to the drawing board to improve the Whipple Shield until the requirements are met. And now, you know the danger of micrometeoroids and orbital debris. You also know how to design a Whipple Shield, and you know how to specifically configure it for your mission. So let's follow up on our initial Starship example, because after we went through this long video, we better understand the problem. The 1mm piece of steel orbital debris can absolutely penetrate the Starship tanks, and I do not think there is a simple solution to this. Starship tanks are really large and will go through extreme loads during the launch and re-entry, which will make it really difficult to include a Whipple Shield. So I think, and I'll be excited to be proven wrong, is that the only way to mitigate the MMOD risk is to keep the stay in low Earth orbit as short as possible. That means that SpaceX will have to do the refueling really fast. On the bright side, they are planning to have the landing fuel in the smaller header tanks, which will be extremely safe because those are placed inside of the larger tanks. The larger tanks here are playing the role of the Whipple bumper. So potentially, the worst case scenario would be cancelled mission and forced landing. What do you think? And this is the end of the deep dive. Thank you so much for watching. Write down your comments, and if you liked it, please subscribe.